Okay.
Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Rene Mendez with us today. Hello, Rene.
Good morning, Frank.
Well, your morning. I
Yes.
guess it's morning for me too. So as long as you're saying that, Rene, what's your geolocation?
Well, I'm currently located in Santiago, the capital of Chile in South America.
Uh-huh. Very
Mhm.
cool. Let's see. And we must be coming into the winter months.
Yes, it's getting cold here, a little bit of rain in the last few days.
Ooh, okay.
You see me wearing
Yeah, you
some
got
coat
you got your
here,
warm stuff on. You got your warm stuff.
whereas you have short sleeves.
Well, let's see. We are entering summer in the Phoenix on this May 21st of 2025 as we record this. And yeah, we are definitely hitting our triple digits temperatures and all that
Mhm.
great stuff. So about 40 C or something along those lines. Um,
Mm.
so yeah, different hemispheres, different ones. Very cool.
Right.
Very nice. And Renee, what do you like to do for research?
Well, most of my career, I have dealt with astrometry.
Mhm.
Astrometry is a branch of astronomy, perhaps the oldest branch of quantitative astronomy,
Uh-huh.
and it deals with the very precise measurement of positions and motions and distances
Yes.
to celestial objects.
Mhm. Very
And
cool.
lately, I have been doing
Nice.
binary stars, and multiple stellar systems as well. I mean, that's one branch of my research. And then I also have I really like mathematics, and so I have been collaborating with some electrical engineers
Cool.
doing applying information theory to several methodologies, including astrometry and photometry.
Very nice. Very, very nice. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one.
Mhm,
Southern binaries with the Zorro Speckle camera at Gemini South. And Renee, take us away.
mhm. Yes. Well, as the number implies, this is a paper on binary stars, observed with a specific camera at the Gemini 8.1 meter telescope, Gemini South.
Mhm.
Gemini, as the name implies, has two telescopes, two twin telescopes, one in Hawaii, one in Chile.
Yep.
And for this particular paper, we have been observing southern binaries with Gemini South.
Cool.
Um, Binary stars are very important for astronomy for the reasons that I will be explaining later on. And I wanted to point out that this is a collaborative research with my colleagues Andrei Tocovini.
Mhm.
He's an expert on speckle imaging.
Mhm.
He's a staff astronomer at Cerro Tololo, specifically provides support for the SOAR telescope.
Nice.
And he is an expert also on binary and multiple stellar systems.
Cool.
Edgardo is a colleague of mine here at the astronomy department at the Universidad de Chile, and Maximiliano was a student of us, a
Ah,
graduate student, now doing his PhD in the UK.
oh, very
And he
good.
provided a lot of support for the writing of this paper
Very cool.
as well.
Good
Mhm.
shout out. Good shout out. Okay, let's get into it. Let's go.
Yeah, as I mentioned, binary stars are really important because if it weren't for binaries, we will not be able to know one of the most important properties of stars, which is their mass.
Hmm.
Luckily, nature has provided us with these wonderful labs, binary stars, which through Kepler's laws basically allows us to determine a very elusive quantity, which is the mass of the stars.
Yes.
When you look at the stars, you receive electromagnetic radiation, which you can measure and quantify,
Yes.
but the mass is kind of hidden. You cannot measure it directly.
Yes.
So you have to resort to the motion of binary stars to determine or to infer the mass of these systems.
Yes. Okay.
Yeah, and mass, as I said, mass is a very important quantity because it determines basically the whole life of a star, how it's
Yes.
born, how it evolves, and how it dies.
Okay.
And one of the most important predictions of the very successful, by the way, theory of stellar evolution is the existence of a relationship between mass and luminosity. And this is very, very important because when you observe, for example, a galaxy, you determine the light, the overall, the integrated light of the galaxy.
Yes.
But what you really, really want, as the song goes, what you really, really want is the mass, because the mass is what it determines the dynamics of the galaxy as a whole.
Yes.
And to go from light to mass, you need to know or to have a very precise prescription for the mass to luminosity relationship.
Yes.
And one of the problems we have is that the mass to luminosity relationship has been determined rather precisely only for solar type stars, but not for stars deficient in metals,
Yes. Okay.
which many galaxies have. I mean, they are deficient in metals. So we don't really know how to go from luminosity to mass in those galaxies.
Okay.
And one of the objectives of this whole research is to define the mass to luminosity relationship for low metallicity stars.
Okay. Good. I'm with you.
Yeah. So we started this project in about 2019. It's really a follow-up in a way of an earlier project that we had started with a similar Speckle camera at the Zorro 4.1 meter telescope.
Okay.
But we realized that there were many systems that we could not resolve because the binaries were too tight.
Okay.
And what happens is that the angular resolution using these techniques depends on the aperture of the telescope. Okay, the
Yes.
larger the aperture of the telescope, the higher angular resolution you have. Okay. So for those systems which we could not resolve at the Zorro telescope, we had to resort to a larger telescope, and that's why we moved to Gemini, which is an 8-meter telescope. So by doubling the aperture, we double the angular resolution, and we are able to look at binaries that are tighter in a way. And why is this important, particularly important for low metallicity stars? Because the stellar density of low metallicity stars is very low in the solar neighborhood.
Yes.
So we have to start looking at larger and larger volumes to have enough low metallicity stars, which means larger distances, which means that you need to have higher angular resolution to resolve them. Yes. So this is the basic motivation for this whole research.
Excellent. Yeah. Very good. I'm with you.
So we, as I said, our sample was based basically on stars that we could barely or not resolve with the Zorro telescope.
Okay.
And at that time, we also started a collaboration with Dr. Elliot Horch from Southern Connecticut State University, who had started a similar campaign using Gemini North. And he was kind enough to share some targets that could be observed with Gemini South. Good. So our initial list was based on the targets that he provided, plus our own targets derived from our Zorro program, plus objects from the literature.
Yes, always literature.
Yes, exactly. Yeah.
Okay. Very good.
So as I said, if you can move on, we can look at the table with our observing log. We already discuss a little bit about the selection of targets. So this is a program that we started in 2019. We as Chilean astronomers are in a fortunate situation that we can apply to the 10% reserve time for Chilean astronomers. So we have a
Nice.
lot of access to the wonderful facilities that the US and also the Europeans have installed in the north of Chile.
Yep.
So we applied to this time. We were very successful. We obtained quite a bit of observing time,
Yeah.
as you can see on the table throughout those years,
Yeah.
usually very well ranked by the time allocation committee.
ATAC.
And we got lots of data on our binary stars throughout that time.
Very good.
Um,
Cool.
so that table shows, for example, one interesting aspect of that table is the very high completion rate, which you can see on the column in that column. That shows that we basically got all what we asked for, and this is
Yeah.
because we were very, very highly ranked by
Yeah.
the TAC, and therefore when put on the queue, these observations were given high priority.
Nice. Very good.
Yeah.
Yay, TAC.
Uh-huh. Right. Okay. If we move on, I mean, speckle interferometry is a very specific technique. Basically, what you do is you take lots of frames in succession at very high speed, because what you want to do is to sort of freeze out the atmosphere.
Yes.
Okay.
Yes.
Freeze out the fluctuations in the atmosphere. And that requires that you have to take very short exposures of a few milliseconds of time.
Yes.
And you take about 1,000 frames, one after the other in a few minutes. And then you combine this data using some of the techniques that I will be describing shortly. And there are a few cameras of this kind installed at big telescopes.
Yep.
One of them, as I mentioned, is the HR cam on the Zorro 4.1 meter telescope, and the other one is installed in Gemini South. It's called Zorro. By the way, there is a similar camera on Gemini North, which is called Alopeque. Alopeque means fox in Hawaiian, and Zorro means a fox in Spanish. Okay.
Cool.
So we have a Hawaiian and a Chilean fox.
Very nice.
They're twin cameras. They're quite similar.
Very.
And these cameras have special detectors that allow us to take very, very quick frames. I mean, it's basically like movie-like, more or less, okay, at very high rate, with the purpose of freezing out the atmosphere, as I was explaining before. And because, I mean, some people have asked me, how come you're observing such bright binaries with a huge telescope? And the reason is because the exposure times are only a few milliseconds of time. So even though we have a huge piece of glass, we're collecting relatively few photons because the integration times are extremely short. Okay. So that's the reason. Well, Zorro is an excellent camera. It was it was provided by NASA as a visitor. The formal name is Visitor Resident Instrument at Gemini South. Okay, it's a visitor instrument, but it's permanently mounted at the telescope.
Everybody uses it. Okay, we'll call it a visitor. Everyone's a visitor.
Well, there are lots of aspects on data reduction and calibration. I don't want to go into the boring details of that, but perhaps you can look at the figure that shows more or less the structure of the data reduction. By the way, this data reduction pipeline was adapted from a similar pipeline that was drafted by Dr. Tocovini. And then we adapted it to the structure of the Zorro data. Okay. So you start with at the top on the left, you start with the data queue. So this is the 1,000 images taken one after the other of a few milliseconds each.
Uh-huh.
Well, that's ingested into the pipeline, and through some algorithms, basically what we do is to compute the Fourier transform of the image
Uh-huh.
from the image space to the frequency, to the spatial frequency
Spatial
space,
frequency. Yeah, yeah. Uh-huh.
to clean up the images, to get
Yes.
rid of unwanted frequencies, and to
Yes.
recover the signal from the binary system, or sometimes multiple system. Okay,
Mm.
and the rest of the pipeline basically deals with log keeping. Okay, log booking. I mean,
Yep.
maintaining, keeping track of the time of observation, the position in the sky of the target, and so on, the sky conditions, and the filter, etc.
Yes.
And at the same time, the pipeline allows you to do a fitting on sometimes the direct images or the fringes that come out of the Fourier
Right.
images, Fourier transform images, to allow basically to determine actually three quantities of interest. One is the separation between the two components of the binary in the
Yep.
sky in arc seconds, the position angle with respect to a reference line, which is usually the north-south line.
Okay.
So this is an angle measured in degrees or radians, and the brightness difference between the primary and the secondary,
Okay.
which tells you how much fainter is the companion with respect to the primary star. Okay, this is very important to be able to characterize the companion.
Okay.
Yeah.
Yes.
So this is all logged into the off-res box there at the bottom,
Mm-hmm.
where you store all these quantities that came out of the feed, and then you correlate this with the two blue blobs there, WDS and BB6. What are these? WDS is the Washington Double Star Catalog,
Yes.
which is the most authoritative source of information regarding all known ever published binary stars in the
Very
world.
cool. Good.
Maintained by the U.S. Naval Observatory in
Yes.
Washington, D.C. by Brian Mason. They're
Yes.
doing a wonderful job. And a very intensive work, because there is a lot of data being published on binaries, and they have to keep track of all that.
Topic these.
And we also ingest into OPS-RES the BB6, which is basically the catalog of orbits for those binary systems which have computed orbital parameters, to compare our observations with the ephemerides that come out of BB6, which is also maintained by the U.S. Naval Observatory.
Makes sense.
And when we do this correlation, then we come out with the final data tables, which is the product that emerges from all this activity, and which are part of this paper as well.
Okay. Cool. I'm with you. Very good.
Mm-hmm. Yeah. Okay, if we move on, in the paper we describe at length all the reduction process, the structure of the pipeline, and so on.
Mm-hmm.
Because actually there aren't that many pipelines that do this kind of work. So, it's very important. And the purpose of this paper in general was more data paper, in the sense of describing the quality of the paper, of the data, the performance of the instrument, how we did this calibration, rather than focusing on the science that comes out of that. Because that will be done in a future paper, okay, in an upcoming paper.
Absolutely.
Of course, done by a graduate student.
Of course.
Okay. So we also describe how we do the fitting of the binary components and so on. It's quite technical stuff. The whole pipeline is written in IDL. It's available, but it's not a commercial software, our pipeline. I mean, so in the sense that we cannot provide support for all solutions that people or all applications that people might have.
Yeah.
So you will have to advance at your own risk if you want to use this pipeline.
Caveat emptor. Yep.
But it's all code available, but it runs on IDL, which is a commercial software. Okay.
Correct. Yep.
Okay. I mean, to show you some of the capabilities of the instrument, here we provide some examples of the autocorrelation functions of basically the Fourier transform of the images, where you can see the central peak is the primary, is the position of the primary star.
Yes.
And then you see some fringes, right? The white kind of stripes on the sides,
yes,
which shows the presence of a companion, and the sort of the orientation or the position of the fringes with respect to a vertical line, for example, indicates the position angle. And the distance between the central blob and the fringe indicates the separation. It's an indication of the separation of the binary component. And in particular, here to the left, let me see. I'm looking at the paper myself here.
I understand.
It's
21 milliarc seconds on this one, and
yeah, it's 21 milliarc seconds, which is a very small separation. It's close to the limit of separation, which is around 27 between 17 and 20 milliarc seconds for the wavelength in which we observe and the aperture of the telescope. So we see that we can clearly detect fringes even down to these very small separations, and which testifies the quality of the images and the data that can produce Zorro. It's a very nice instrument.
Very cool. Yeah, and so the top one I think is blue, and then the second row is red. Okay.
Right.
A little tighter there. Okay. Very cool. Okay, those are outstanding power spectra. Very good.
Yeah, and then let's see the following figure. Yeah, no, this is an example of some artifacts that from time to time appear on the data. You know, the dots, top and down, exactly those two dots are is extra power on the power spectrum due to vibrations, kind of random vibrations that happen probably from the support structure of the telescope.
Okay.
Yeah. The same as the ring that appears on the right image. Okay. But in both cases, in any way, in both cases, you can clearly detect the fringes, even though we have this extra noise coming from this. We could not really detect any systematics in terms of the telescope vibrating at the specific frequencies. It can probably depends on where the telescope is pointing out, in the sky.
Yes, you know? It might be angle dependent.
Right. I mean, there are also probably mechanical issues. You know, in at some point, it's not all software. You know, at some point,
at some point, it's a real piece of hardware, and
exactly, and it's a heavy telescope which you have to drive at a very specific speed, and so you know sometimes well, we see the same kind of features on the SOAR images. Yeah, I mean this is not that common.
Yeah. Okay? Yep. Hardware rattles.
Right. And okay, one of the critical aspects for our research is having a very good calibration
Yes.
astrometric calibration.
Yes.
Because, well, this instrument has two channels, a blue and a red channel for which you get simultaneous images. And because the filters have different thicknesses
Okay.
and
Uh-huh.
the
Uh-huh.
cameras are not exactly the same and so on,
Okay.
um, there might be also slight differences in the focal distances involved.
Yes.
The the
Yes.
pixel scale, I mean, how many arc seconds in the sky represents one pixel might be slightly different between the blue and the red channel.
Okay.
And we have to take care of that.
Yes.
Okay. And we took care of that by comparing precisely the separation. For example, for a given observing run, we compared the separation of the on the blue and red channel for all the binary systems,
Yes.
and we put all the measurements into a common system, that of the blue
Yes.
channel.
Uh-huh.
Okay,
Uh-huh.
so that's the first calibration that has to be taken care of.
Naturally. Uh-huh.
And then you don't know exactly how the camera is pointing to the sky. So the orientation of the north celestial pole, for example, might not be exactly aligned with the X or Y axis of the camera
Oh,
because
sure.
because
Uh-huh.
the camera is put on the telescope and not directly on the sky. Okay,
Right.
so
Right.
so you have to take care of also of that of that effect, and you don't know a priority. I mean, based on first principles on optics, you can kind of compute the plate scale. I mean, how many arc seconds per pixel there are on the camera, but
Yes.
it's a first approximation. The real truth comes from actual measurements.
Yes, it does.
So exactly. So in order to determine that plate scale, what we do is to look at binary systems which have been followed up for many, many years, and which have excellent measurements.
Okay.
And we compare our measurements with the predictions from those orbital solutions.
Yes.
And from that, then we're able to correct, sort of speak, the pixel scale, which, remember, it was at this stage on a common scale between the blue and the
Blue and
red
the
channel.
red. Yes. Okay. Cool. I'm with you. Mm-hmm.
Yeah. I mean, this was a very laborious and delicate
Yes.
work.
Yes.
And by the way, it has to be done independently for each observing run, because
Ooh.
at the beginning they mounted and dismounted the
Ooh.
Zorro camera from the telescope, and of course, when you unmount it and mount it again, does not necessarily go into exactly the same mechanical position. So
Yes.
you have to do the calibrations every single time.
Wow.
Okay.
Wow. Okay. All right.
So yeah,
A lot of
and for
work. A lot
example,
of
yeah,
work.
it's a lot of work. Yes, and it's very specific to find to do very precise and fine relative astrometry.
Yes.
Okay.
Mm-hmm.
So in the plots that you're showing there, we show the comparisons on the left, the ratio between the red and the blue channel, and as you can see, it's not a one-to-one relationship, which shows that there is a plate scale difference between the blue and the red channel,
Yeah.
which has to be corrected for. Okay,
Yes.
this is an example, but we did this for all the observing
All of them.
runs.
Yep.
Okay. And to the right, you see the ratio between the Zorro and the SOAR
Oh, yeah.
solution for our
Okay.
binary stars
The Everest. Okay.
in terms of separation, the top panel,
Okay.
and in terms of
Position
the
angle.
position angle at the
Yeah. Okay.
lower panels.
Okay. All righty. Right. Generally pretty good. Got an outlier here, down here.
Yes, there are a few outliers.
But generally
Yeah,
good.
but what we do is in general, we do what's called sigma clipping. So you define a certain maximum sigma excursions that your data can take,
Okay. Yeah, yeah.
and then you compute sort of average, a sigma, and then you exclude all
Yes.
the measurements that are outside the sigma clipping that you have specified, and
Yeah.
you recompute again the mean and the sigma, and you iterate until convergence.
I'm with you. Cool.
So, for example, the dashed red lines there show the sigma clipping that we apply to this data.
Yes. And that's why they're all in there. Okay. Very good.
Yeah.
So
yeah, and then when we put all of this in action, if you go to the next to figure 6, you can then have an idea of the comparison between our measurements, our Zorro measurements, with the SOAR measurements done for this very same systems. The SOAR measurements are in green. The Zorro measurements, the Zorro Gemini measurements in red, the red triangle. And older data, but still interferometric data of very good quality are the black pluses. And as you can see, the Zorro data follows pretty well. You can see it in the inlet. The inlet shows it's a zoom of that particular segment of the orbit. Okay, one important point is that, as you can see on the bigger figure, this orbit is not by all means an excellent orbit, okay, because we don't have a lot of measurements on the rest of the orbit.
Yes.
We only have observed this in a portion, but we don't care. We only care about having a good correspondence between the SOAR and the Zorro data.
Yes.
Locally at the time of observation. And if later on, suppose in 20 years from now, somebody really solves this orbit at an exquisite level, then we can come back and recalibrate all our data with those new orbital parameters.
Yes.
See what I mean?
Yes, I'm with you. I understand.
And one of the difficult issues in binary, in this type of binary star research is the inexistence, basically, of very good calibrators to determine the very exact, the very precise plate scale. So we do the best we can, okay, but it's perhaps not the best. It's not optimal, but it's the best we can do with what we have now.
There you go. That's all you can ask for. Yep. Very nice. Beautiful. Beautiful.
Yeah. If we move on to some of the diagnostic plots later on, so what we have is we have been observing we have been observing binaries of different separation throughout a range of epochs and on different filters. So we can do all kinds of tests, intercomparisons. For example, looking at the measurements of a particular pair throughout time in position angle, in separation, in photometry, to detect outliers, and mostly to determine empirically what's the quality of the data. In the end, the best way really to quantify the precision of a measurement is to make lots of measurements of that quantity, to compute its mean, and to look at its variance. Okay, so this is what we do with this kind of plots. Okay.
Very good. I'm with you.
This also allows us to pinpoint outliers and to try to explain. Most of the outliers can be explained for various reasons, which are explained in the paper. A few of them, unfortunately, for a few of them, we don't have an explanation for the reason them being outlier. Very few. But most of them can be explained either because the companion is too faint, or it's too close to the
Close.
primary.
Yeah.
I mean, there are a number of reasons for that. Okay.
Very cool.
So
I want
yeah,
to let's I just want to show this table. I want to take a look at this.
yeah. I mean, exactly.
So
Yeah,
here's our resolve
maybe
systems.
so. So this is the end product of our research, really, that comes out of the pipeline. It's so it shows the identification of the target, WDS, the discovery. Oh, sorry, the radio just turned on. Let me turn it off.
Okay. Well,
Just a second.
we got a little extra entertainment here. All good.
um, Sorry about that.
All good.
Um, uh, um,
And this is
And
only part of the
so
table.
so it shows the epoch of the observation, the filter,
Mhm. Yes.
the number of cubes, data cubes that were involved in the determination, the position angle, the separation, the uncertainties on those two quantities,
Okay.
the brightness difference, and then a bunch of diagnostics. This data is all available for people who may want to look at some of these binaries. Yeah.
Yes, this is only part of the table, people.
Yes, yes.
The rest of it's online.
Mhm.
Okay. Very cool. Let's rotate that back out. Go to here. Okay.
Yeah, I mean, as I said, these figures are all part of the assessment of the internal precision of the measurements.
Uh-huh.
Um, as a general statement, we can say that the precision of this data is around 1 milliarc second.
Yes.
The
Yes.
separation, which is very good, is very
Very good.
good.
Yeah.
Um, I
Nice.
mean, for the non-experts, 1 milliarc seconds is the size of a person standing on the moon.
There you go.
So
That's impressive. It's very impressive.
it's impressive. Yes, indeed.
Okay.
Um, I mean, to give you an idea, the Zorro telescope, which is half the size, the typical uncertainties are more on the order of 3 milliarc seconds.
Okay.
So this is a factor
Factor
of three
three.
better.
Nice. Very
Yes.
cool.
And then we corroborate this by looking at the O minus C's, which is
Mhm.
observed minus computed differences for two astrometric calibrators, which corroborates basically our estimate of the precision in position angle and in separation. Okay.
Yeah. Yep, I'm with you. All right. Mm-hmm.
Yeah, and then later on there is a histogram that shows it's an over further below. I think it's
Mm-hmm.
uh,
We get into the
figure
preliminary orbits.
11. I think
Right.
it is.
These are the positional
Um,
errors,
this
checking
is
for
the
errors.
precision that has to do with the photometry. Yeah, that histogram shows you. This is an overall picture of the sample
Right.
in the sense that it shows the number of systems which we have been able to resolve and study with Zorro as a function of separation in the
Wow.
sky.
Cool.
And then the inlet shows the tighter systems, sort of speak, those that have very small separation.
Ah, there we go. Okay. Mm-hmm. Yes.
For the whole sample as it stands right now.
Very nice. Okay. Yeah, the average. Okay.
And I think the following figure, it's also interesting from the point of view of characterizing the sample because it shows, it shows the brightness difference between the primary and the secondary component. So this shows that this instrument is capable of detecting binaries which have up to 6 or 6.5 or even 7 magnitudes of difference between the primary and the secondary. So you are able to determine, suppose you have a solar type star, you can determine a companion that it's a very low mass star next to it. okay,
Fair enough. Yeah.
by being able to detect a very faint companion,
Okay.
which is one of the. I mean, this was actually one of the science drivers for building this instrument,
Yeah.
which we are applying now to binaries, but which can nevertheless also be applied to the search for exoplanets, for example, or
For
other
example,
massive
right.
bodies.
Because you got a great contrast there. Mhm.
Exactly. Yes.
Beautiful. Really nice instrument. Very nice.
Um, yes, and in a way, I mean, speckle interferometry. It's a poor man's version of typical intensity or phase
Oh,
interferometry because it allows to have
yeah,
um,
right.
really, I mean, diffraction limited resolution at optical wavelengths, which is extremely difficult and
It is.
expensive to do otherwise.
Yep. Yep. That's a nice analogy. Very good. Uh-huh. Yeah. Beautiful.
Okay. Yeah, those plots are again diagnostics. A bunch of objects were not resolved, as shown on that table. We tried them, but we couldn't resolve. The non resolutions are not definitive because, for example, the object could be going through periastron.
For example, yes.
Exactly, and then they're too tight. We cannot resolve. But if we wait a little bit, when it goes through apoastron, perhaps we can detect the secondary.
Mm-hmm. Mm-hmm. Good project for the future. Okay.
Exactly.
And these are
And so this, as I said, the purpose of this paper was not to come up with orbits for all of the systems, but at least show some of the capabilities. And here are two examples. So these are very tight binaries. As you can see, on the axis there, we're talking about a few milliard seconds of separation.
yes.
Um, that's why the points seem to be a bit scattered. But if you
Right.
look at the axis, you realize that these separations are extremely
It's
small.
small.
Okay.
Yeah.
Um, this will be impossible to do with anything but an 8-meter telescope. And so I have a graduate student now that it's working with us, and she will be looking at all these systems in a lot more detail. Also combine radial velocity data with imaging data,
Cool.
okay, to
Good.
have full
Good.
solutions for these systems.
I predict an awesome thesis there.
Yeah, we hope so too.
Cross fingers. Yeah, very good. Okay, we got
Um,
many orbital
and
elements for one of them.
yeah, these are the numerical values of the orbital elements for
Mm-hmm.
the orbits that
Yeah, it's a
we
W.
just saw. In
Mm-hmm.
comparison with whatever is available on the literature, we're doing relatively well there, which shows the robustness of our
Okay.
solutions.
Very.
Um, and Yeah, I mean, one of the surprises that what we found is
Yeah.
um,
PSF.
yeah, I mean, one of them is this very tight binary system. But further on, we show the detection of extra companions that we were not known before. The C companion there. So you see
Yes.
the primary at the center, the B companion. Usually you get two images. There is an ambiguity in the resolution of the
Oh, yeah.
images
180.
for
Yep.
using
Yep.
this technique
Yep.
because we lose the phase. We lose the phase of the image, so we don't know in which quadrant is the
This way or
companion.
this way. Yes. It's the ambiguity
Yeah.
in the sign there. Mm-hmm. I'm with you.
But
But
we are
here's a
able to
discovery.
detect the companions, and here you see a much fainter companion, the C companion, that seems to be moving in the same way as the B companion, as
Right.
the
Triple system here.
arrows indicate. And this system, for example, would be extremely interesting to study in terms of its dynamical stability
Yes.
with further observations.
Right now that we know that C exists, we can go after it.
Exactly.
Very cool. Nice discovery. A triple. Woohoo.
Yes.
HIP
Um,
57421. Very nice. Okay, 16.
Yes, and then we
Spectrum.
show various other systems.
Mhm.
You This is again this is um, a triple system. So you see the fringes that go
Any
like
fringes.
this. Okay, very equally spaced and
Yes.
showing the large separation system.
Oh,
And then you see a pair of fringes like this at very large distances from the primary, indicating
ah,
a very tight
uh-huh.
inner system. So
Right.
this is also a triple system.
Hierarchical.
We cannot resolve the image of it, but we can see it in the fringes.
Yes. Hmm. Hierarchical triple. Mhm.
Exactly, a hierarchical triple, of
Mhm.
which we have several in our sample.
Those are interesting. Binaries are interesting too. Triples are interesting as well. Very good.
Even more fun.
For different reasons, but yes.
Difficult to model, but
Right.
very interesting from the
Right.
dynamical point of view. So here you see another one. Here to the left, you see the two extremely uh,
Done.
well separated fringes of the inner companion, and then all the other fringes indicating the same position angle
Oh yeah.
of the wider
Oh
separation system.
yeah. Okay, I see it. Uh-huh. Uh-huh. Yeah, good. Okay.
Yeah, basically that's it. As I said, this is a data sort of data reporting paper that we really wanted to publish to highlight the extraordinary capabilities of Zorro. At the same time, it allows us to show the time allocation committee that we're doing
We're
something
doing
with
it.
data.
We're using it well. We're using it well.
No, I think really that's important. I need to
I'll
show
come back to
that.
that. Yeah, yeah. I'll come back to that point. You're right. It is important, right?
And this justifies also the application for more telescope time. So so
Exactly.
now we have something to show, and that allows us to keep on observing some of these systems.
Very cool. Very cool. Renee, I want to thank you so much for walking us through your very awesome article. Very nice. Thank you
Thank
so
you.
much. Yeah. Let's see. And you kind of touched on it a little bit there toward the end. So let me go ahead and push on it a little bit.
Mhm.
Where do you think we go from here, given the published article? You already mentioned you have a grad student who's already going to be taking a look at some orbits and, adding in additional data to that. But is there more observing campaigns one could do? Is there additional improvements to the pipeline that may occur? This kind of stuff. So just sort of next steps. Where do you think we go from here, given the published?
Right. Yes, absolutely. Uh, we have an observing campaign to determine radial velocities for all of these systems, because when you combine radial velocities with astrometry, you're able to determine individual masses of both components at a very high precision.
Yes.
Okay.
Yes.
So we're observing these systems with a high resolution spectrograph.
Okay.
We're going to have radial velocities for all of them. This is ongoing work.
Nice.
In fact, our graduate student is dealing with this data. And for those systems that have periods short enough that merit further observations soon, for sure we're going to put a new observing proposal for Gemini.
Yeah.
And also adding new potential low metallicity systems
Yeah. Right.
um,
Hmm.
to be included in this
Hmm.
upcoming proposal.
That's so
Some
we
of
can
the
get that.
systems that were published in this paper have very long periods, so it doesn't make any sense to keep on observing them. You have to wait, I don't know, 5 years, 10 years, or whatever, until you have a substantial motion. But for the short period system, especially these hierarchical systems,
Yeah.
it's
Yeah. Yeah.
worthwhile to do relatively quick follow-up.
Okay. Nice. Very cool. Very cool. And I think you have a little something to share for our future astrometericists. So let's go ahead and put that up.
Right. Well, if you're watching this video, you probably have some interest in astrometry. So I wanted to highlight this book. It's not such a recent book. It has a few years already, but it's the latest book
Oh.
on astrometry, as the name implies, astrometry for astrophysics. The editor was my advisor, my thesis
Ah,
advisor, Professor William Alalte.
okay, okay, okay. Yeah,
Uh,
yeah.
he's now retired. He's living in Argentina now. Yeah, he went for the better weather than New Haven. I got my PhD at Yale. He was a faculty member at Yale University.
Very cool.
Um,
Right.
Anyway, this is a very interesting book because it's at the graduate level. It's for people who have an interest in the specific technical and methodological details of astrometry as applied to various problems in astrophysics. It's
Indeed.
from Cambridge University Press. And I just checked on the web page, and it has um, 5,000 PDF
Downloads.
downloads.
Yeah, nice. Hmm.
Actually, 6,000 now, and total views more than 7,000 views. So it seems to be
Getting
a
out there.
well appreciated textbook.
Hmm.
It's really in the form of a textbook. So
Very cool.
I encourage people who are interested in astrometry to look at it.
Absolutely. Absolutely. Because we have to wait a little while sometimes for the systems to get in a better orbit. So, yeah. Very cool. Thank you for sharing that.
Mhm.
Yeah, that was really great. I want to thank you again, Renee, so much for walking us through your very awesome article and the chapter in your book there. Thank you.
Thank you very much for your interest and willingness to do a little bit of advertisement of our work.
Absolutely. Absolutely. Love to do it. And that will do, everyone. And I hope this made your astrometry astronomy day just a little bit better. And we will see you on the next one. Bye bye.
Bye bye.